Nuclear binding energy is the amount of energy required to separate a nucleus into its individual protons and neutrons, and it equals the mass defect converted to energy by Einstein's formula. Think of a nucleus like a tightly packed group of tiny magnets that stick together because of a special strong force, and the binding energy is how much work you would need to pull those magnets completely apart. When protons and neutrons come together to form a nucleus, the total mass of that nucleus is a little bit less than the sum of the separate parts. That missing mass is called the mass defect, and it has been released as energy when the nucleus formed. You can calculate the binding energy by multiplying the mass defect by the speed of light squared, which shows that even a small mass difference corresponds to a large energy. Larger binding energy per particle generally means a more stable nucleus. So nuclei around iron are the most tightly bound and stable. Many students think binding energy is a force and try to add forces instead of using energy and mass concepts, and the fix is to remember it is energy required, not a push or pull. Another common misconception is confusing total binding energy with binding energy per particle, and the simple way to avoid that is to always check whether you are dividing by the number of nucleons. A third mistake is forgetting to convert mass units correctly when using the formula, and the best practice is to use consistent units and convert mass to kilograms before multiplying by the speed of light squared, or to use atomic mass units with the appropriate energy conversion factor. For more videos and resources on binding energy and related topics, check out www.gumballdegree.com.